Hello, I'm Zach Olson,
And I'm Adam Berger.
and this is Fun with Physics.
In the game of
Pool.
Before we start with the physics of pool, we first have to know the history. Zach, care to enlighten us on the history of pool?
Indeed I do, sir. Pool has a very long and rich history, beginning in the 15th century. The game has been played by everybody, be it royalty, presidents, the middle class, the poor, mental patients, or criminals. Pool began as a lawn game, similar to croquet, played sometime during the 15th century in Northern Europe. It was also played in France and has evolved from that point into present-day style of the billiard pool table and its rules. The game moved indoors to a wooden table with green cloth to simulate grass, and a simple border was placed around the edges to keep the ball in play. The balls were originally shoved rather than struck with wooden sticks called maces. That's a cue stick. The term billiard comes from the French terms billard, meaning wooden stick, and bille, meaning ball. When the ball got close to the rail, it was quite inconvenient to use a mace due to its large head. So in the 1600s, the cue was invented to lessen the difficulty of hitting the ball in a tight situation. In such a case, the players would turn the mace around and use its handle to strike the ball. The handle was called a cue, meaning tail, which is from where we get the word cue. I know, they sound the same. Still, for a long time, only men were allowed to use the cue. Women were forced to use the mace because it was believed they were more likely to rip the cloth with the cue, which was sharper. Billiard pool tables originally had flat walls for rails, and their only function was to keep the balls from falling off. But billiard players discovered that the balls could bounce off the rails and began deliberately aiming at them, thus the bank shot was created. This is where the billiard ball is hit towards the rail with the intention for it to rebound from one or more cushions as part of the shot and into the pocket. And now that the history of pool is over and done with, Adam here will explain to us the rules of pool.
Indeed I shall. The game of pool starts with the cue ball placed on one side of the table and the other 15 balls on the other side. The game begins with what is known as a break. The break happens by one of the two players hitting the cue ball into the triangular setup of the other 15 balls. From there, the players take turns trying to sink their assigned balls, striped or solid, into the pockets around the table. Players are assigned their type of balls near the beginning of the game. Excuse me. When both players try to sink the easiest shot. The type of ball pocketed first becomes the objective of the player who sinks it. The other form of ball becomes the other player's objective for the rest of the game. Players continue their turn until they miss a shot, sink the other player's ball, or scratch. Scratching happens when the cue ball is pocketed during one of the turns of the two players. After scratching, the cue ball comes out of the pocket it was pocketed into, if the cue ball went in at all. There are several types of scratching that will not be depicted in this demo, and placed on the break side of the table, or in other words, the side in which the cue ball was placed before the break. The cue ball can be placed and played from any position on the break side of the pool table, behind the second diamond on the side of the pool table. After the cue ball is placed, the player must hit the ball in the direction the ball was hit during the break, also referred to as the direction of the break. The 8 ball is a new and final objective that is achieved by the player after he or she sinks all of his/her assigned balls. The 8 ball is the last of the pool balls to be pocketed. If the 8 ball is pocketed before a player has sunk all of their assigned balls, they automatically lose the game. When a player is in position to sink the 8 ball, they must call a pocket for it to go in, and they cannot scratch. If a player forgets to call the wrong pocket for the 8 ball, they lose. If a player scratches during the break, or scratches while attempting to sink the 8 ball, they also lose. The only way to win is to successfully pocket the 8 ball without scratching or miscalling a pocket after pocketing all of the player's assigned balls.
Okay, now that the rules and history of the game are done, I think it is time for an example. Do you agree, Adam?
I do agree, Zach.
Well, let's go.
Let's play.
Okay. You may begin.
Want me to break?
Yes. Now, none of you may have thought about this, but there were quite a few forces that acted throughout the entire shot, from before contact, to motion, to contact, to even now. There are forces acting on each and every ball. But for now, we will focus on the forces acting on the cue ball. Currently, there are two forces acting on the cue ball. There is the gravity force, which is pulling the ball down and keeping it on the table, and the normal force, which is pushing off of the table. And the reason these forces don't make the ball move is because they are equal and opposite, so they cancel out, rendering the ball motionless. Now, when Adam hit the ball, he gave the ball what is known as an applied force. That is when the ball is hit and it begins to move. The reason the ball eventually becomes, stopped is because of a friction force in the opposite direction that will slow the ball down over time or until contact is made, in which friction, no matter what, is still always slowing the ball down. Actually, I think it is my turn. So
No, I made that in.
just give me the stick. Okay, so let's put some math into this. I'm sorry to now start to bore all of you, but I think it's necessary. So, say I am now to take my shot because it is my turn. Say I manage to get my shot level, an angle of 0 degrees, with the ball and strike it with 11 newtons of force. Now, if the ball weighs 0.18 kilograms and the coefficient of friction is 0.01, what is the total force that ends up acting on the ball? In the meantime, I'll do this motion, and you guys can, put the process and think about what the answer is. Once I am done, we will give you the answer. Hey, you got something in.
It appears you're solids.
Mm-hmm. Okay, here you go.
Thank you. Kill it.
Did you figure the answer out yet? Well, if you haven't, here it is. The answer is 10.98 newtons. Now that sounds pretty similar to my original shot power, doesn't it? Well, I guess with the very small coefficient of friction that existed, it really wouldn't slow down too much, now would it? Well, that's all that comes to my mind for now. Adam, if you would like to take your shot now, we can keep going.
Wait, Zach. It's your turn.
Oh, okay. Sorry about that. Does that mean I'm solids?
You are solid, sir.
Well, then I guess I'll take another shot.
You got mine and yours in.
Cool. Well, wait. As for the rules you said, I made one of yours in. It is now your shot.
It is, sir. But first, let's explain the physics behind this shot, shall we?
There's more physics?
There is more physics, Zach, believe it or not.
No way!
Yeah. It's
Well?
called impulses and momentum. Do you know what that is?
You're going to have to elaborate there, sir.
Okay, well, I'll let you know. Momentum equals mass times velocity of an object. The impulse is the change in momentum.
That's going a little far. I think you're going to need to give us an example so we all understand what you're getting at here.
You think we need an example?
I'm pretty sure we do, because I'm still lost and I'm right here.
Did you know that impulse also equals force times time?
No, I did not. See, you learn something new every day.
So if impulse equals force times time, right?
Yes.
Doesn't impulse equal the change in momentum? So doesn't the change in momentum equal force times time?
I guess it would.
It does, actually.
Wow.
Yeah.
That's quite interesting.
So let's go for an example now, shall we?
Think we should.
Okay, Zach. Let's say that the mass of the cue ball is 0.18 kilograms.
Sounds good.
Seem fair? Good.
Mhm.
Now, the The force I applied to the cue ball is 24 newtons,
Well, that's a quite bit more than my shot, don't you think?
for obvious reasons.
Thanks.
Anytime, buddy. The time the cue stick is touching the cue ball is 0.028 seconds.
That's a small time.
Quite fast.
Indeed.
But let's think about it. How fast do you think the cue stick touches the cue ball? Quite fast, right?
Mm-hmm.
When I take my shot, so it seems fair.
It does.
With this information, we can figure out the impulse of the cue ball and also the final velocity.
We can.
We can. Using the equation, force times time equals mass times final velocity minus mass times initial velocity.
Well.
Yeah.
Can you guys figure it out?
Go ahead, try to figure it out.
In the meantime, I think we shall continue our game.
Yes, we shall. Sorry, Zach, I'm Stripes, right?
I think so.
Thank you.
Let me get this out of the way for you.
Oh, thank you very much, sir. Oh, you put me in a bind, sir.
Mm.
I have no choice.
Oh.
I can't believe that worked.
Lucky you.
Yes.
Did you guys figure it out? Well, in case you haven't, or if you have and you want to make sure you're right, Adam here will tell you the answer since this is his example.
The answer to this, the final velocity of the ball, is 3.73 meters per second.
Wow. That's quite fast.
I go hard.
Yeah, nice. You have me beat, sir.
Yes, I do. It's my turn again?
I think it is.
Oh, it appears I made another shot.
Okay, come on.
I'm sorry, sir. I'll stop.
Well, that was one of mine.
I think I got your ball in, Zach.
Now, thank you.
I believe it is
Thank
your
you.
turn.
I guess that does make it my turn, and gives me a small advantage. But wait, I think I'm beginning to remember that there is more to your impulses and momentum than we have told them so far.
Really?
Yes.
What is that?
It is known as the conservation of momentum.
The conservation of momentum. What's that?
Well, it is when there's the object in motion. In this case, the cue ball. Right here. And it's moving because, well, one of us has hit it. When the point when it makes contact with another ball is an impulse, like you said,
Mm-hmm.
but the conservation of momentum also takes place. Being that, it is possible that once I hit this ball, after they make contact, we can figure out, the speed of either ball after contact from with the information we already know.
I don't know about that, sir. That's going a little bit out of the lines, don't you think?
Well, not necessarily, but the fact that it is the conservation of momentum, it has to be the same from start to finish, because momentum cannot be destroyed or created until another force comes into play.
So you're telling me there's a law of conservation of momentum?
Yes, it's a law, and if you break it, you won't go to prison because, well, it's not in our Constitution, but it is a law nonetheless.
So you really can't break it?
You cannot.
Thank you.
You're
Now
welcome.
I understand.
Okay, now, as I said, we can figure this out. So, since it's my shot, well, let's say I shoot the ball, and say, once again, the weight is 0.18 kilograms. And the speed I hit it at is 1.6 meters per second. Yes, I know that is a number smaller than yours, but come on, just work with me.
There's a workout machine
Okay.
right there, sir.
Thanks. Okay, so,
That's funny.
obviously, the ball I'm hitting is not moving, so its velocity is 0.
Right now.
As of now, both are. But once I take my shot, the ball I hit will have a velocity of 0 until contact is made.
Makes sense.
Now, once contact is made, we can figure out the velocity of either the cue ball or the ball I make contact with.
Impossible.
It is. In fact, why don't we let them have a chance to figure it out?
Go ahead. Figure it out.
In the meantime, I'll give you a visual of this conservation of momentum. Well, that's disappointing.
It appears you scratched.
Yes, it appears I have.
Now, according to the rules of pool, I get to place the ball behind this diamond on the break side, correct?
In this table it's a circle, but yes. Go for it. Okay, well, now that my moment of depression is over, have you guys come up with the answer? Well, if not, sorry, I'm going to give you a little bit of a spoiler alert. Here it is. The velocity of the cue ball ends up becoming 0, which means it will stop upon contact. While the second ball, due to the conservation momentum, must have a speed of 1.6 meters per second because the momentum must remain constant from start to finish.
So you're telling me that the velocity I hit this ball will be transferred to this ball?
Well,
if I were to hit this ball?
Yes, in an ideal state, the cue ball would stop upon contact.
Oh.
Granted, there's a whole bunch of other little details here and there that make that not happen.
Like
but
friction, but
yes,
we can ignore that
for
this
now we
purpose.
can. But in an ideal situation, the cue ball should have stopped and, well, I wouldn't have scratched.
Ah,
So, physics was on my side, but your table's not.
I understand.
Yeah. So, well, with that, I think we should continue playing for a little bit. You know, we do have a game to finish.
Indeed we do.
Okay.
Move a little bit this way. Nothing went in.
Well, I guess we have to keep going then.
It's your turn, Zach.
Yes, and good move there. Okay. Well, let's go. Oh, I scratched. Hey, I put something in at least. But it is your shot, sir.
Is it?
Yes, I did scratch.
I didn't notice.
Disappointing.
I'm gonna go for this pretty black ball. Oh no!
You know, the number on the
I
black
won.
ball no, the number on the black ball is 8.
Oh no!
Now, if you remember from our rules introduction, if you sink the 8 ball without all of your assigned balls being sunk, the other player wins. So, I thank you, good sir, but you gave me the game. It's been a pleasure.
Pleasure to play with you, my friend.
Thank you. Better luck next time. And with that, this was Fun with Physics in the game of Pool. When the ball got close to a rail, it was quite inconvenient to use a mace due to its large head. When the ball got close to the rail, it was quite inconvenient to use a mace due to its large head. So in the 1600s, when the ball got close to the rail, it was quite inconvenient to use a mace due to its large head. So in the 1600s, the cue was invented to lessen the difficulty of hitting the ball in a tight situation. When the ball got close to the rail, it was quite inconvenient to use a mace due to its large head. So in the 1600s, the cue was invented to lessen the difficulty of hitting the ball in a tight situation. Women were forced to use the mace because it was believed that they were more likely to rip the cloth with the cue. Women were forced to use the mace because it was believed... Women were forced to use the mace because it was believed that they were more likely to tear the cloth with the cue. Women were forced to use the mace because it was believed that they were more likely to tear the cloth.
During the break of the break, also referred to as the direction of... So Zach, let's say that the mass of the cue ball is 0.18 kilograms, okay? Let's also say the force applied to the cue ball is 24 newtons, okay?
Well, that's a lot more than my shot.
Well, indeed it is. Now, what do are you doing? Now, Zach, let's say that the mass of the cue ball is 0.18 newtons, shall we?
Well, not newtons, so cut.
Oh, wait.